All right, so yesterday in class we finished up talking about preparation of acid halides, and the easiest way to make an acid halide is to take a carboxylic acid and treat it with thionyl chloride. When you do that, the reaction goes forward because you're driving off sulfur dioxide gas. And the overall mechanism is fairly steppy. It's one of the more complicated mechanisms that we'll see in these last few chapters. So you may want to practice drawing this out a few times just in case it does show up on one of the exams. I did note too at the end that quite often the base that you use is pyridine because it's a good base and a bad nucleophile, meaning it'll soak up any of this hydrochloric acid that's generated during the reaction, which is necessary sometimes. Does anybody remember the abbreviation for pyridine? PYR. So if you ever see PYR, that's basically just indicating that you have some sort of base around, well, in this case, pyridine, that's going to be soaking up the HCl in this reaction. All right, now we need to look at reactions of acid halides, and luckily, a lot of this is going to look very familiar. And the first one is hydrolysis. All right, and so hydrolysis, we're going to obviously treat the acid halide with water. So if you have water around, water is a weak nucleophile. But like I said, if you have a weak nucleophile, you can counteract that by having a really, really strong electrophile. So in this case, water can actually react with this just simply because the electrophile is so strong. So the water will attack in, will kick up electrons onto that oxygen. Like I said, don't show this as an SN2 substitution. You have to show the tetrahedral intermediate. So when you do this, you now have oxygen with the negative charge. Got chlorine down here. The water that added in has a positive charge. And really quickly, in the next step, this oxygen can clamp down and kick off the chloride. And then last but not least, you're going to do a proton transfer, where this final product, it's going to lose that proton coming off the end, and you're left with a carboxylic acid. So the reality is we can go back and forth between both of these. I could theoretically go back in a circle and make my acid chloride, and what reagent do we need again? If I wanted to go from the carboxylic acid back to the acid halide? SOCl2. So a lot of these can be done back and forth, depending on which direction you really want to go. Does that make sense? The next one is very, very similar. This is called aldehylysis. Does not roll off the tongue well. You think you've had that before? Maybe a rough Saturday morning. Get some greasy eggs. All right, and with these reactions, same thing. You've got a really, really good electrophile. You've got your alcohol floating around, and typically these ones are run using pyridine to soak up any of the excess acid and to facilitate proton transfers. And you can imagine you're going to swap out that halogen for your new alcohol group. So essentially you can convert this to an ester really easily. The key thing is identifying the correct alcohol that you want in order to swap out that specific side. Does that make sense? The mechanism is very similar, so I'm not going to redraw it a dozen times for you to see. All right, the next one is with amines. This one's kind of nice because you don't have to have pyridine because amines themselves are a base. But if you have an acid chloride and let's say excess ammonia, So I'm going to indicate excess here. The excess ammonia can actually act as its own base. So you can imagine you could easily swap off that halogen for an NH2 group and make an amide. Conversely, if you do this same reaction, with the primary amine, you'll get an amide that is now functionalized. And lastly, if you use a secondary amide, you can get a more functionalized, secondary amine, you can get a more functionalized amide. I will say that this isn't a common reaction that chemists do anymore, so let's make a note. And we're actually going to come back and cover this later. And I'm just going to say this reaction is old school. Newer/better techniques are available. And so we typically don't see this very often in a lab setting, but if you're in an absolute pinch, it's something you can do. The reason that this reaction is a lot more, or not as commonly used anymore, is it's actually possible to combine a carboxylic acid and an amine to make an amide, which is a lot easier to carry out than to have to convert your carboxylic acid to an acid halide and then react it with an amide. It cuts down one of those steps. So I will say better techniques are available for that reaction where you want to form an amide. Does that make sense? I know it's frustrating that the book shows a lot of these old reactions, but you might see them on the ACS, so I feel like I got to show them to you. The next one is a reduction. And the reduction reaction, again, isn't super common because you can reduce the carboxylic acid, but I'll show it to you anyways. Let's say you want to convert this to a primary alcohol. What reducing agent do you think we need if this is similar to a carboxylic acid? LAH, absolutely. So LAH also works on this. And then in the last step, you typically need some sort of weak acid or water workup to convert it all the way to the alcohol. Similar to the last one, you don't see this very often because it's simply easier to reduce the carboxylic acid and not have to hassle with this. Does that make sense? Sometimes people will get stuck on this though. So I do want to show you the mechanism. And I'll show you the question that students often have. So lithium aluminum hydride, I'm only going to show the anionic part, looks like this. First step is going to be the hydride attacking in, kicking up electrons. Have an oxygen with a negative charge, your chlorine and your hydrogen. Then in the next step, this clamps down. Can end up forming a hydride, an aldehyde. However, this is really reactive. Meaning it's hard to stop here. Typically, when you run this reaction, you can't even stop here if you try. So in the next step, you'll keep on reducing this with your excess lithium aluminum hydride all the way to your alcohol. But chemists don't like being told that they can't do something. And so what do you think an alternate technique could be to stop at the aldehyde? Does anybody have an idea? Yeah, do something with the LAH. So maybe limit it. That could be one idea. If you try to limit it, you still run into problems. The main problem that you run into is this is simply too nucleophilic. The hydride source really, really wants to attack a carbonyl. It's one of the strongest reducing agents we've seen, right? So another option might be to limit the nucleophilicity, right? So the question is, how can we limit a nucleophile's strength? Who remembers from first term? Sterics, absolutely, right? So if you're bulky, you're not going to be a good nucleophile. And that's what chemists did, was they said, can we find any alternate reducing agents that are really bulky? That way we can slow it down and make it a worse nucleophile. So let's take a look at that. So how to stop at the aldehyde. The key is you got to bulk up. And I was reading a book about some of the early chemists that were working on things like this, and quite often they would test literally tens of thousands of reagents trying to figure out the one that worked the best. I'm not going to explain why it worked the best. It just worked the best, and we're going to leave it at that. But the one that they found looks like this. And as you can see, it is mighty bulky. It's got these 3 tert-butoxy groups coming off of the aluminum and a hydride kind of snuggled in between them. So you can imagine this isn't a good nucleophile. In fact, it's a really weak nucleophile. And what this is called is lithium tri-tert-butoxy aluminum hydride. You can imagine that's quite the mouthful. So usually you'll see this abbreviated as LiALOTBU3H. Or, yeah, that's not really a whole lot better. You might see LiALOR3H, where the R is a placeholder for the tert-butyl group. So you might see this one of 3 different ways in your textbook. But the key is it's so bulky, it's not a good nucleophile. And will only reduce acid halides. Does that make sense? It's just that steric bulkiness really slowing it down. So I'll show you an example of this in action so you can kind of see why this is useful. And in this example, we've got multiple functional groups that we have to worry about. But let's say I want to convert this starting material to an alcohol, but I want to leave the ketone as is. Or sorry, to an aldehyde, not an alcohol. How might I be able to do that? We can't just throw in sodium borohydride, right? That'll reduce the ketone. We can't throw in LAH, it'll reduce both of them. We want to selectively reduce the carboxylic acid over the ketone. So one option would be to react this with thionyl chloride. And if you do that, you'll selectively convert your carboxylic acid to an acid halide. And then in your next step, you could reduce that with our special reducing agent. There's also another way to get here. So let's take a look at the second way. Does anybody know an alternate route? I'll just do a green pathway. This is going back a few lectures. I'll give you a hint. What happens when you treat this with BH3THF? Which one? Yeah, it selectively will reduce the carboxylic acid. The ketone will be completely untouched. And then how can we get to our final product using the green route? PCC. So then the question comes, well, why would we choose the blue route over the green route? Does anybody know from a practical sense? PCC will give you cancer. I would prefer not using it. So in this case, the blue route avoids that harmful chromium-based reagent. Like I said, in chemistry, there's often multiple routes to get to the same product. And as a chemist, it's kind of up to you to choose which one's cheapest, greenest, easiest to carry out, and less harmful to everybody, the community, the chemists, the lab mates, things like that. So there's a lot of different things you have to factor into when you're planning out a synthesis. All right, there's a couple more nucleophiles we need to look at. And this is the reaction with carbon. And the first carbon nucleophile we've seen quite a bit is with Grignard reagents. So we'll start with that one. It's pretty simple. If you have an acid halide and let's say methyl magnesium bromide, you can add in a methyl group and convert this to a ketone. However, just like with the aldehyde before, it is hard to stop here. And that's due to the nucleophilic nature of Grignard reagents, right? They're really strong nucleophiles, and so they can't stop easily. They end up overshooting. And then in step 2, you treat this with water, and we know with aldehydes and ketones, you can add in more Grignards. Oh, sorry, that should be a methyl group. And you can end up making a tertiary alcohol that way. So that's kind of review of what we've been seeing. But like I said, chemists are never happy being told they can't stop somewhere. And so they wanted to figure out a better way to do this. What's the way we can make something less nucleophilic? Make it big, bulk it up, right? And that's where the new reagent comes into play. And this new reagent is called a Gilman reagent. And this is an organocuprate. And the key with the Gilman reagent is you've got more bulk. So let's say you've got your acid halide, like this. This time we've got, a central copper atom that's covalently bound to lithium. And then this copper has 2 R groups. So in this reaction, the R groups act as the nucleophile. And this is nice because it's bulked up. It's going to have a harder time attacking that electrophilic carbon. And if you think about the dipole here between the carbon and the copper, it's not going to be nearly as strong as between a carbon and a magnesium atom. So it's not going to be as nucleophilic. I'm not going to show the full mechanism for this. I don't even think the book shows it. But the nice thing with this is that you can stop at the ketone. you won't overshoot and go directly to the alcohol. Does that make sense? All right, I'm going to do a little bit of a side note. And this is going way back, and I've seen quite a few people try to do this on exams, which is why I wanted to show it. I see a lot of students on exams try to use a Grignard reagent to do SN2 chemistry. The reality is this leads to a mess. Grignard reagents are not good at SN2. And the reason for this is Grignard reagents are also really, really strong bases too, which leads to a lot of elimination products, which we don't want, right? If you want a substitution reaction, you want to avoid elimination. However, the Gilman reagent is quite nice. So let's say you have R2CuLi, that's our Gilman reagent, and you've got something like an alkyl bromide. All of a sudden you can swap off that bromine, for one of those R groups in the Gilman reagent. So this is a much better route that is more commonly seen. Does that make sense? All right, what I like to do in this chapter is kind of pause and make mini reaction maps because there's so much going on in this chapter. So the most important one, in my opinion, is the reaction map for acid halides because it's the most versatile carboxylic acid derivative. So what I'm going to do is make a map with acid halides in the center. And then I'm going to put other various functional groups around it, and then we're going to connect it with arrows. But the more you fill these in, the easier it is to get good at remembering the reagents. And let's see, put an alcohol down here. I'm going to put an aldehyde down here. I'm going to put a tertiary alcohol down here. Put a ketone over here. Put a carboxylic acid over here. So you can see we can interconvert between our acid halide and a ton of different functional groups. So let's briefly review. How can we convert an acid to an acid halide? Thionyl chloride, exactly. So SOCl2 is common. What about if we want to go in the backwards direction? Yeah, just water. You can also add in acid too, that can help facilitate that nucleophilicity. All right, how about going from our acid halide to an ester? I'm going to make this R prime too. Just need an alcohol, right? And quite often this is done with pyridine, so you can convert an acid halide to an ester that way. All right, what about going from our acid halide to an amide, specifically this first amide in the top right-hand corner? Just need excess ammonia, right? It's one of the old school reactions. The other two are very similar. Oops, this should be H2NR. And this should be excess, not gas. And then this one should be HNR2 and excess. And you can make all three different amine types that way. All right, What about going directly to an alcohol? LAH, exactly. So we do LAH for step 1, and then step 2, you can react it with something like water or weak acid. All right, what about going from an acid halide to an aldehyde? This is the alphabet soup one. This is our LiAlOR3H. So that's a bulky reducing agent where we can stop there. And then what about a tertiary alcohol? Grignard. So we can go R prime MgX. That would be step 1. And then step 2 would be treating it with something like water. And then the last one, if we want to go to a ketone and not overshoot, that's when we use the Gilman reagent. And that would be R2CuLi. That's how most books will show it. And I'll make it R prime just so we can keep track. Does that make sense? It's a lot of reactions. Some of you have asked me why I don't have the flashcards up on the website. I would encourage you to make your own flashcards for these just so you can see them over and over and over again. All right, let's try a challenge problem. I think we've got enough time. Our goal is to start from benzene and only using the chemistry we know and any other building blocks we need, we're going to try to make a drug. This is one of my favorite drugs. This is ibuprofen. All right, so see if you can figure out all the steps you need in order to get from benzene to ibuprofen. And there's multiple routes. So I'll give you guys a couple minutes to work on this. This one's fairly tricky, so what we may do is work through this slowly as a class, and I'll get us started with the first few steps. First step I would maybe consider for this one would be to react it with ethyl chloride and aluminum trichloride. And if you do this, you can make ethyl benzene. You may run into overalkylation, however, you can try to get as much as possible of the monoalkylated product. All right, what would we need to do to get the other side on? Yeah, and in this case, what I'm going to do is an acylation, and I'll show you why in a second. But we'll try to build our organic framework here. So right now I've got my ethyl group on one side. I'm going to slide this over. Got my isobutyl group off the other side, or sorry, it's a ketone. And now what I want to do is I want to brominate the other position right here. How can I get a bromine to get installed on the benzylic carbon? NBS, okay? So let's go ahead and do that. So we want to start building up off of that next. All right, so I've got a bromine there. I'm going to slide this over. What I want to do next, though, is get rid of the ketone, because we know we don't want that in the final product. How can I get rid of that ketone? Zinc, mercury, HCl. Okay, so that's our Clemmensen reduction. And if you remember in the Clemmensen reduction, you can get rid of that aryl ketone. All right, now the million-dollar question. How can we get to our final product? Do what now? Okay, so we're going to turn this intermediate into a Grignard reagent with magnesium. All right, if we convert that functional group to a Grignard reagent, how can we then turn the Grignard reagent into a carboxylic acid and add our very last carbon? Yeah, carbon dioxide. So toss in dry ice. And then in your last step, you would want strong acid. So this was a bit of review, but oftentimes these synthesis problems involve reactions from this chapter, last chapter, second term, and even back to first term. So try to practice those integrated problems in your textbook. Those are some of the more challenging problems. And there's just synthesis problems built into the chapter as well. But try to do as many book problems as possible.
Could you go over that CO2 step again?
Yeah. So let's go back in our notes. If you remember, a Grignard reagent can actually attack CO2. That installs one new carbon. You get a carboxylate salt. And then if you protonate that, you can end up with a carboxylic acid. So if we look at our Grignard reagent in the top corner versus our product in the bottom right, you notice we added a carbon and we've got a carboxylic acid. It's a really nice way of installing carboxylic acids simply. Yeah, good question. All right, now we've got to jump into our next functional group. We're just going to kind of go down the list. We're going to jump into acid anhydrides. Good thing is most of these reactions are very similar. So first thing we've got to do is figure out how to prepare anhydrides. And there's a couple different ways to prepare them. One of the easiest ways is by using the king of carboxylic acid derivatives, the acid halide, and then a nucleophile that is a carboxylate salt, right? So if you combine both of these together, you can actually swap out the chlorine. I'm going to make that one R prime. And you can use this to make all sorts of different anhydrides. However, in order to do this, you have to use an acid halide. So you use acid halide and then a carboxylate salt. This works well for most situations, but you do have to be careful again of acid being around, so you might run this occasionally with pyridine as well. There are other simpler mechanisms. They're not as common. And synthetically, they're not useful, but I'm going to show you this because you might see it. For simple symmetric anhydrides, you can do the following. You can take your carboxylic acid, heat the snot out of it at 800 degrees Celsius, and actually just force this reaction to go. The problem is most organic chemists are mighty uncomfortable heating anything up to 800 degrees Celsius, and you're very likely to cook everything that you've made. So this really only works well for things like acetic acid or simple acids, and it's typically done under high pressure as well. So it's not useful for synthesis, it's useful for commercial preparation of bulk anhydrides, like acetic anhydride. All right, I'll show you why this anhydride might be more suitable than an acid halide. So anhydrides are sometimes better than halides. And I'll show you a prime example of this. Okay, so let's think about salicylic acid. Salicylic acid is the stuff that's usually found in acne creams. I used to remember this as a teenager because I would bleach all my pillowcases on accident. It's pretty powerful stuff. And what happens, yep, it will kill all the bugs on your face and bleach your pillow. And you can treat this with acetic anhydride. And the nice thing with this is gentle. And will not react with the carboxylic acid. If we treated this with an acid halide, we'd run the risk of accidentally converting that carboxylic acid side into an anhydride itself. And so when you run this reaction, you're actually able to convert the alcohol coming off this position into an ester. All right, so I'm just going to highlight the group that was moved around. In this reaction, we took this acyl group and we ended up putting it on the end of that alcohol there. This is acetyl salicylic acid. We started with salicylic acid, so we just added on that acetyl group. Does anybody know the common name for acetyl salicylic acid? Aspirin. So if you ever want a fun experiment to do at home, you can convert your acne face cream into aspirin, although I wouldn't recommend ingesting it. So it is pretty common for installing acyl groups, especially using acetic anhydride, is you can basically block an alcohol. This is really common in drug manufacturing because acyl groups can get cleaved off in your body, turning an inactive drug into an active drug. So it's a common technique. There's also another one that's very common that uses this exact same mechanism. And I like it because it's a good review of nucleophilicity. Whoops. So para-aminophenol, if you treat this with acetic anhydride, the question is which side will react with the anhydride? Will it be the nitrogen in the amine or the oxygen in the alcohol, and why? So talk with your neighbor and see if you can agree. All right, let's see a show of hands. How many of you think the alcohol will react? How many of you think the amine will react? How many of you didn't vote? All right. So now the big question is, which side's more nucleophilic and why? Let's think about the lone pair. Your lone pair on oxygen versus a lone pair on nitrogen. Which one's going to be more available to attack? On the nitrogen, right? Why is a lone pair on the nitrogen going to be more available for attack? Electronegativity, exactly. Nitrogen's less electronegative, which means its lone pair is going to stick out further, right? That means it's going to be more available to act as a nucleophile than the ones on the oxygen that are being held tightly. So when you do this reaction, you can change the amino group into an amide group and end up acylating it. This is also known as Tylenol. So that's the brand name for acetaminophen, I believe. Like I said, this is one of the drugs that the FDA is getting more and more skeptical of. It's one of the leading causes of accidental overdoses in the United States because the difference between the effective dose and a lethal dose is relatively narrow for a lot of over-the-counter drugs. So especially for kids, they're trying to get parents to consider using alternates than Tylenol. So I think that's where we're going to stop today. Tomorrow when we come in, we'll start off with the reaction map and then jump into esters and probably onto amides after that.